Okay, so let's do this last example here. So it says you throw a ball vertically upward from the roof of a tall building. The ball leaves your hand at a point when the roof railing, or a point even with the roof's railing, with an upward speed of 15 meters per second. The ball is then in free fall. On its way back down, it misses the railing at the location of the building. The acceleration due to gravity is 9.8 meters per second squared. We want to find the position and velocity of the ball at 1 second and 4 seconds. We want to find the velocity of the ball when it's 5 meters above the railing. We want to find the maximum height and the acceleration of the ball when it's at a maximum height. So lots of questions to answer here. First thing to do is to write down our givens. And because there was nothing provided here, we're going to set up our coordinate system. So we're going to put the top of the building at 0 meters. We're going to have downward be the negative direction. And we're going to set up our position and velocity functions. So we'll plug in our given information here. So for our final velocity in the y, our initial velocity was 15 meters per second minus 9.8 meters per second squared times time. And for our position, y final equals, now y initial we set at 0. Our initial velocity was 15 meters per second times time minus 9.8 over 2 times time squared. Again, since we have to answer multiple questions, we're going to put these into our calculator. Get rid of these. So we'll have our position function be the blue line. So it's going to be 15 minus 9.8 divided by 2 times x squared. Need to get an x over here as well. There we go. And then we'll have the red line be our velocity. Okay. And we can actually reuse this. There's y1, so this is going to be our position at 1 second, and then we need our position at 4 seconds. There we go. 10.1 and negative 18.4. Okay, and then we'll do our velocity. So it's going to be y2. So 5.2 and negative 24.2. Okay, and that's A. So B says we want to find the velocity of the ball when it's 5 meters above the railing. We need to figure out when that happens. One way we could do this is with a substitution. Another way we could do it is to solve it as a two-step problem and figure out at what time is the ball 5 meters in the air, and then determine how fast it was going at that time. So we could, on our calculator, solve that. Okay, so we're going to have this. We'll go into our graph. There we go. And actually, let's do this. So we're going to graph the position 5 meters. There we go. So we can see that there are 2 places that this happens. Once on the way up and once on the way down. So it definitely goes higher than 5 meters is something else we've determined. And we can use the calc function to find the intersection. So our first curve is the parabola, our second is the line, and we're going to give it a guess. Bring it over here on the way up. And that's our intersection. So we can use that. Actually, let me delete this. Put this in there. And then we can plug that into our other equation. So that value, time value, is stored in x. So we could actually go back to our velocity function and put in x. That's going to evaluate the velocity function at the time that it's 5 meters in the air and give us a value of 11.27. I'm going to change this to t naught. That's where we want. We've got 11.27 meters per second. Now, on the way back down, the velocity would be negative, and that would be a different time, so we could find that time as well. If we know properties of parabolic motion, then we can probably guess what this value is. It's probably the same value, but negative. But let's just confirm here. So the next time was 2.68, and we'll just go back, do the evaluation again. There we go, we get the same answer, but negative. So positive on the way up, negative on the way down. That's the way that we can solve that problem with a graphing calculator. Now, we could have done this algebraically using this equation, which is the combination of the 2 we were just using. So we could have plugged in our position and solved directly for the velocity. And you'll see that when we solve for our final velocity, there's a square term here. So when we took the square root of that, we'd end up getting a plus or minus sign. So we would not lose that second solution. Okay, so the next question says max height. Now, from calc, there's a couple of things that we want to relate these types of questions to. Max height is trying to maximize the position function. We find maximums by figuring out when the first derivative is equal to 0, and then using the second derivative test to ensure that it's a max and not a min. So let's think about what's going on here. We want a max. We take the derivative of the position function, and that gives velocity. We want to figure out when the velocity is equal to 0. And the second derivative test gives acceleration, and we know that for there to be a max, the curve has to be concave down, which would be a negative second derivative, and we have a negative acceleration here. So that's from calc. Now, from AP Physics C, we talked about this a little bit differently. We said when the object goes up and then comes back down, at its highest point, its vertical velocity is equal to 0 because it's not moving up or down anymore. And obviously, we have an acceleration that's pointed downward. So we kind of, we weren't using the first and second derivative tests, but we conceptually understood what those quantities meant. So anyway, we can find the max height when the velocity is equal to 0. There's two ways we could do this. We could use our calculator, or we could solve it algebraically. Today we're kind of practicing calculator skills, so we'll get out of this here real quick. We'll go into our calculator and graph our velocity. Turn that off. And we should be able to find that 0, so we're going to go to Calc, 0. Let's see where our cursor is a little bit too far down there. There we go. Give it a guess. Yep, and it's about 1.5. We'll say 1.53. And we can also solve this really easily without the use of a calculator. We could have done our final velocity was equal to our initial velocity plus acceleration times time. And we wanted our final velocity to be equal to 0 meters per second. Our initial velocity was 15 meters per second, and negative 9.8 meters per second squared times time. So we could have solved this, and this would have come out to the same thing. And if we wanted to find the max velocity, we could have plugged this in. So the max height, or final max, we would have plugged our time in to our position function, and evaluating it algebraically would give us 11.5 meters. Or another way we could have done it is with our calculator. Can graph that. Go to Calc. And max. And we're going to give it a left and a right bound. Cursors. There we go. And 11.479. So there we go. Now, one thing to keep in mind is anytime we use the graphing calculator to find an answer, it's giving us an estimate, whereas an algebraic solution method could give us an exact answer. So that's just something to keep in mind. Let me show all the work for this here real quick. So we're going to have and we plug in 0 and 15 meters per second times 1.53 plus negative 9.8 over 2 times 1.53. And that would give us our max as well for rounding. For E here, I've added a couple of extra questions, which are just sketching graphs of the motion. So what I'd like for you guys to do is pause the video, sketch these graphs, and then unpause the video and see if you get the graphs correctly. And then I also have one extra question here for you. Find the time when the position is negative 5 meters, or basically 5 meters below the railing. And again, after you do that, check the notes and see if you got the right answer.